So light is not just treated as a particle. We can also treat light as an electromagnetic wave, a combination of electricity and magnetism. When we do this, we label light with the Greek letter lambda. Lambda represents wavelength. And I know that wavelength is equal to the speed of light in a vacuum, c, divided by f, which represents the frequency of light. And I can draw a picture of a light wave by drawing kind of this x and y axis, and it kind of just wobbles up and down, kind of in a wavy shape. The distance from the peak to another peak, that is what we refer to as wavelength. The height of this wave from the middle point, we call this the amplitude. Kind of how fast the wave is wiggling back and forth, we call that the frequency. And they're all related to each other by this equation, this lambda equals c over f. And it works in particular for light. So there's another equation we can use to figure out the wavelength of light outside of a vacuum. Wavelength of light will change when you're traveling inside of different medias. So lambda sub n is equal to lambda divided by n, where this n represents an n from previous work that we've done, represents the index of refraction. So it's specific to a medium that you're traveling through. This discussion of light as a wave has very specific applications. It has to be used when light is interacting with small objects or when wave characteristics must be used. And this happens in the fields of interference of light and diffraction of light. So we need to know more about both interference and diffraction to really understand how light works. Now, the word diffraction simply refers to a bending of light around some kind of barrier, and it's based on a principle called Huygens Principle. Huygens Principle says that every single piece of a light wave is its own tiny little wavelet that kind of radiates out little wave fronts. So every point of a wave is a wavelet. We can kind of draw what this looks like. So if I have a bunch of points on a wave that's traveling forward, each one of those little points radiates outwards, kind of like a little pebble that you might drop into a pond. You see little ripples come out. That is what's happening for a wave. Every single point on this wave is its own tiny little pond ripple. And those ripples combine with each other, and they interfere with each other. And this is what we call interference. And the definitive experiment that shows this is called the Huygens double slit. And Huygens double slit is proof that light can act as a wave. And it depends on light interfering from wavelets from two slits. So if I take light and I pass it through a tiny little slit. So here's my two little slices. Here's my slits. And I'm going to pass light through these. I can define some things. I can define the distance between those slits as the letter D. And I have a wave that comes in. So maybe a light of blue wave that comes in here. And when it hits these little slits, that light radiates outwards like ripples from a pond, from two little pebbles. In some places, these two little pebbles combine together and give me striped bright bands. And some places, they kind of interfere with each other and they give me dark bands. And if I set up a screen far away, I'm going to see the influence of those bright and dark bands. So I'm going to see a bright band and then a dark band, which I'm not going to draw because it's dark. And we have another bright band and all these little bright bands. And as I go further from the center, the bright bands get a little bit dimmer and a little bit dimmer. Okay? And I can label these bright bands. This very middle bright band, I call M equals 0. That's the brightest band of all. The second bright band, I call M equals 1. And the same thing underneath. So I have two M equals 1 bright bands. Then I also have another bright band, M equals 2. And I have two of those, and M equals 3, and so on and so forth. Those are all the bright bands that I get. And then I can define an angle. So from my middle bright band, and we'll do this in a bright popping color yellow, to my first bright band. So I can draw a nice right triangle. We love right triangles in physics. We draw them all the time, all over the place. And the angle from that middle portion up to my first bright band, I call theta. Using all these variables, using this d, this order, and this theta, I can define an equation that lets me figure out where I get all of my bright bands. And I can figure out where I get my dark bands. And those equations, if we shrink this down and make a little bit of room, we get a bright band following this equation. M, the order number, times lambda, the wavelength, is equal to d, the slit separation, times sine of theta, the angle between your bright spot, the central bright spot, and the order. So to remind us, M represents something called the order. And it's going to start out with 0 for the central bright band. It's going to be above and below, plus or minus 1. There's going to be 2, or it could be 3. Those could represent the orders, all the way up to however many orders you have. D is the distance between your slits, so how far apart your two little holes are. And then theta is the angle between the order and the central bright band. We also have destructive interference. So these bright bands represent what we call constructive. And then we'll have dark bands. So let's try to be consistent. We'll have dark bands that represent destructive interference. So that's where you're not going to have light combining together to give you bright stuff. You're going to have actual darkness. And the dark bands, we can predict where those are with a similar equation. M plus 1/2 times lambda is equal to d times sine of theta. So if we were to draw a representation of these two, in constructive interference, let's draw two wavelengths. I have a wave going up, then down, then back up. And then I have another wave coming from another slit going up, then down, then back up. And if I draw a little diagonal line seeing what's lining up, I can see the peak with the peak and the trough with the trough. So when I add these two together, I'm going to get a wave that's actually going to be double the size. So I get twice as high and twice as low. So my wave gets bigger, it gets brighter. With destructive interference, I have this situation. I have a wave that goes up and then down and then back up. And the other wave goes down and then up and then back down. So if I draw diagonal lines to see where my peaks line up, I can see that I have a peak right here meeting with a trough down here. So if I add those amplitudes together, add those heights together, and I'm going to do this in a different color, the total is actually going to cancel out and I'm going to get 0. I'm going to get nothing. Thus we have destructive interference versus constructive interference. Now when I have multiple slit diffraction, we can get something else that's happening. We can have something called a grading. So this is when I take multiple slits and line them up right next to each other. In multiple slits, I get a process called, instead of interference, I get something called diffraction. I'm going to get a whole bunch of bright bands and a whole bunch of dark bands, and I can describe this diffraction pattern using the following equation, using m lambda equals d sine theta. So multiple slits, I can predict these bright spots in diffraction. Again, this is slightly different than the Young's double slit experiment because in this we have a grating, something called a grating, which is just basically a series of double slits, a whole bunch of double slits. And I can only find the bright spots when I'm working with multiple slits, when I'm working with a grating. We also have single slit diffraction. So this is light bending around a single slit. So to kind of see what the difference is between these two. In the double slit, I had 2 slices. In the multiple slit, I have a whole bunch of little slices. I have all of these little spots where light is going to form a wavelet. So my pattern gets a little complicated there. For a single slit, I have a single slice. There's no interference opportunity because I only have one place where light can come through. However, I still get a pattern. I still get light bending around the single slit. And we call this single slit diffraction. Now, in single slit diffraction, I use a different equation. I use the equation m times lambda equals big D sine theta. So you'll be tempted to think that this is exactly the same as the multiple slit equation. They look very, very similar. But in this case, our m's are orders, and they're equal to above and below, kind of positive and -1, positive and -2, positive and -3. We notice that we don't start at 0. There's no m equals 0 order for diffraction. No central order. And D is not the separation of the slits, not the distance between them. D is actually the slit width, how wide your slit is. So those are the basics of what we really need to know to understand wave optics, diffraction and interference.